There is no need to freak out. That's why we are here, to help you find eigenvectors and eigenvalues of a matrix. Let's see an example. Let A be the matrix 1, 2, 1, 0, and let's find the eigenvalues first, and then eigenvectors for each one of those eigenvalues. To find the eigenvalues of a matrix, we need to find what we call the characteristic polynomial, which is just the determinant of A minus lambda times the identity matrix. In this case, A minus lambda times identity is A minus lambda times the identity, which is this matrix. So now let's take the determinant. The determinant will be 1 minus lambda times minus lambda minus 2 times 1. And if you simplify, that's lambda squared minus lambda minus 2, which you can factor that quadratic polynomial. It has two roots, minus 1 and 2, so it factors as lambda plus 1 times lambda minus 2. But the important part is that there are two roots, minus 1 and 2, and those are the eigenvalues. So the first part of the problem is done. The answer is that there are two eigenvalues, lambda equals minus 1 and lambda equals 2. Now we have to find eigenvectors for each one of those eigenvalues. To find eigenvectors attached to a particular eigenvalue, we're going to find a basis for the kernel of A minus lambda times the identity. So, for example, for lambda equals minus 1, we're going to find, first of all, what is A minus 1 times the identity. That is the matrix 2, 2, 1, 1. And then we have to solve for the kernel of that matrix. So we're going to do row reduction to get a simpler matrix. I'm going to replace the first row by the second row, then subtract twice the first row from the second row, and I get 1, 1, 0, 0, and that is already in row reduced form. That tells me that the solutions of the kernel will satisfy x plus y equals 0. So that is a one-dimensional kernel, and it has as a generator, for example, v1 equal to 1 minus 1. This is an eigenvector. Now, is it really an eigenvector? Let's check. We can multiply the matrix by that vector, and we are hoping we get a multiple of that vector. Let's see it. This matrix times this vector is the vector minus 1, 1, which is minus 1 times the original vector. So that means that 1 minus 1 is an eigenvector with eigenvalue minus 1, so we win. Now, for lambda equals to 2, I do the same thing. I have to find the kernel of A minus 2 times the identity, which is that matrix over there, and then I do row reduction, and I get the matrix 1 minus 2, 0, 0. That implies that the vectors in the kernel satisfy that x minus 2y equals 0, so it is a one-dimensional kernel, and one generator is, for example, v2 equal to the vector 2, 1. That's another eigenvector. Is it really an eigenvector? Trust but verify. So let's check that it is an eigenvector. Multiply the matrix by the vector. I get the vector 4, 2, which is twice the original vector. So that means that it is an eigenvector with eigenvalue 2, which is what I wanted to find. So now I have found my eigenvectors. So my final answer is that there are two eigenvalues for this matrix, minus 1 and 2, and the eigenvectors for each one of those are 1 minus 1 and 2, 1. The eigenspace generated by lambda equals minus 1 is one-dimensional, generated by that one vector, and the eigenspace generated by lambda equals to 2 is also one-dimensional, generated by that other vector. So this is the final answer.